Welcome back to Cosmos Unlocked. In the last episode, we uncovered the secrets behind the universe's ultimate speed limit, the speed of light, and how it shapes everything from time to space. But what if there's more to the story? Think about it. Why is the speed limit of the universe set at its particular value? Currently, no theory provides an answer. A universe with a higher speed of light would have weaker locality, while a universe with a lower speed of light would exhibit stronger locality. Such a universe wouldn't be impossible in theory. In physics, there's no inherent reason for the speed of light to be exactly one specific number. Perhaps we simply happen to measure it as 300,000 kilometers per second. This value feels incredibly fast to us, yet for interstellar travel, it's painfully slow. Fans of the Three-Body Problem series might remember a concept from the third book, the idea of setting an extremely low speed limit for light within the solar system, such as 10 meters per second. In this scenario, the solar system becomes so restricted that humanity could never escape it. At present, we don't know why the speed limit has this particular value, but we can make some guesses. Perhaps it's the only possible value, with the speed of light reflecting some fundamental truth about the universe and space-time. For instance, if space-time is quantized, the speed of light might arise from how information transfers between adjacent quantum nodes. Much like the thickness and tension of a guitar string determine the speed of waves along it, the speed of light might work similarly. Perhaps one day, we'll discover a unified theory of spacetime that explains why light and information travel at specific speeds, providing answers to all these questions. Another possibility is that the speed of light is just a positive number between 0 and infinity, without a particular reason for its value. A speed of 0 corresponds to a universe with no interactions, while infinite speed implies a completely non-local universe. If the speed limit could be any positive number, why is it this one? We don't know. Perhaps the speed of light isn't universal, it might only apply to this part of the universe, resulting from how spacetime condensed after the Big Bang. In other regions, the speed of light might be determined by random quantum processes, meaning other parts of the universe could have entirely different speed limits. On this note, let me recommend a science fiction trilogy I particularly love, Zones of Thought by Vernor Ving. The trilogy includes A Fire Upon the Deep, A Deepness in the Sky, and Children of the Sky. It presents a bold concept: the universe is divided into 3 zones, each with different speed of light limits. These include the normal speed of light in our region, a higher speed in another zone, and an infinite speed in the highest zone. In the books, the author compares these zones to the Earth's sky, ocean, and deep sea. For beings from the high-speed zones, falling into our slow zone is terrifying. What would take days to cross in their zone might take centuries or millennia in ours. The trilogy builds countless worlds based on this grand concept. It's too long to discuss in detail here, but I highly recommend reading it yourself. Returning to the topic of light speed, since we don't know why it's the way it is now, how can we be sure it won't change in the future? Or that it was always the same in the past? While we can't travel through time to verify these questions, the universe has provided us with a beautiful ancient astronomical museum, the night sky. When we gaze at the night sky, we're not seeing the present but the past. The farther away an object is, the longer its light takes to reach us, and the older it appears. By observing more distant objects, we can explore the past. When astronomers study the orbits, collisions, and explosions of celestial bodies, they find no evidence of stars violating the universal speed limit. That tells us about the past. Predicting the future, however, remains a daunting challenge. We can boldly predict the future based on 14 billion years of history. This seems reliable, but it assumes that the universe has always operated in the same way in the past and will continue to do so in the future. However, this is purely a hypothesis. We know that the universe has undergone several completely different periods in the past, such as the period before the Big Bang, the inflationary period, and the current expansion period. What information do we have to suggest that the universe won't change in the future? As we mentioned earlier, just as logic is the foundation of science, believing that the universe will continue to operate in its current state is also a fundamental scientific assumption. If we insist that the universe could be completely different tomorrow, light speed changes, the nature of space changes, then science itself would become untenable. Speaking of light speed, we can't avoid discussing faster-than-light travel. Let's end by talking about this fascinating possibility. The idea of light speed travel captivates us because of humanity's desire to explore the cosmos, to land on unknown planets, visit distant stars, and even meet alien civilizations. Who wouldn't want such an opportunity? But if you dream of boarding a spacecraft to visit other galaxies, the speed limit of the universe will be a heartbreaking reality. After all, the nearest star to the solar system is 4 light years away. However, perhaps we're asking the wrong question. Instead of asking whether we can surpass the speed of light, we should ask whether we can reach distant stars within a reasonable time frame. These two questions are not equivalent. Light speed is the fastest you can travel through space, but as we discussed earlier, space itself is not just an abstract backdrop, it is a dynamic entity that can expand and contract. This brings us to the key point: if we could compress the space between us and a distant star, we could reach it within a reasonable amount of time without needing to travel extremely fast through space. Is this achievable? The idea might not be entirely far-fetched. While we don't fully understand the nature of space-time, we do know it can be warped or compressed. Unfortunately, doing so requires an enormous amount of energy. To compress space for interstellar travel would consume an impractical amount of energy. Another way to shorten the journey is by using wormholes. Under certain conditions, two very distant locations in the universe could be connected by a wormhole, allowing you to travel from one to the other. In science fiction, traversing a wormhole is often depicted with flashing lights and loud, booming sounds. In reality, no one knows what passing through a wormhole would actually be like. It might be no different from walking through a door. Indeed, if space has more than 3 dimensions, some places that seem far apart in 3-dimensional space might actually be adjacent in higher dimensions. Imagine the universe's space as a roll of toilet paper, with space layered upon itself. Traveling along the paper might seem like a long journey, but if a wormhole pierces through the layers, distances that appear vast could suddenly become very short. This idea might sound fanciful, but it doesn't conflict with any current physical laws. Unfortunately, all calculations so far suggest that wormholes are unstable. They may collapse in an instant. In other words, even if we were to discover a wormhole, it might disappear before we could use it. Furthermore, since we live on the surface of this rolled-up paper rather than outside it, we don't know how to construct a wormhole or where it would lead. It's like hopping into a stranger's car in Beijing and expecting them to take you to Shanghai. At this point, you might feel a little disappointed. We start with dreams of faster-than-light travel but end with a dose of cold reality. Still, let's set aside practical considerations for now and let those pesky details not disrupt our ambitious plans for interstellar travel. Compressing space or traversing wormholes remains an enormous challenge, but we can still find hope. Physicists have turned interstellar travel from completely impossible to very hard and expensive, which is progress. When it comes to the distant future of technological development, predictions might hit the mark or become a joke. So, we won't make any bold predictions. However, humanity's history seems to suggest that miracles lie ahead. And since no fundamental physical laws prohibit interstellar travel, we can still hold on to that hope. This episode has largely focused on the limits of light speed, but let's end with an exception. Physics is very cautious about the extremely small. Natural laws often seem to have loopholes in very small spaces. If you were a lawyer specializing in natural laws and reviewed them closely, you might notice that the speed limit refers specifically to the speed of light in a vacuum. Why specify in a vacuum? Because the speed of light depends on the medium through which it travels. In air, glass, or water, the speed of light is slower than in a vacuum. This is because photons take time to interact with particles in these mediums, reducing their overall speed. So, can light's speed be surpassed? The answer might be yes. Here, surpassing doesn't mean exceeding 300,000 kilometers per second, but rather refers to particles traveling faster than photons in certain mediums. While this speed never exceeds the vacuum speed of light, for example, a high-energy muon can travel faster than photons through ice. Strictly speaking, this is indeed motion faster than light. High-energy muons exhibit a remarkable property: they can travel close to the speed of light in any medium. This phenomenon leads to an interesting effect. Imagine a boat on a lake moving faster than the waves it creates. Those waves would overlap to form a dramatic wake. Similarly, a plane moving faster than the speed of sound produces a sonic boom. When a muon travels faster than light through ice, what happens? It creates a light boom, known as Cherenkov radiation. Sonic booms are fascinating phenomena, but we won't delve into them today. Feel free to look up sonic booms of supersonic planes to learn more. Once you understand sonic booms, you'll better grasp the light booms created by muons in flight. Physicists often use the faint blue glow of these explosions to detect such particles and measure their speeds. In other words, if the universe, or a local part of it, were filled with ice, you could technically move faster than light. Of course, this doesn't mean surpassing the speed of light in a vacuum, but rather slowing light down to achieve this effect, which is a bit of a loophole. That wraps up our discussion of light speed. The topic often sparks debates. For example, people often ask, we measure the speed of light as it is now, but how can we be sure we won't exceed it as technology advances? Explaining this clearly isn't easy. It involves the very nature of light, which isn't like a bullet flying from one point to another. Measuring its speed is not as simple as dividing distance by time. This topic could easily fill an entire episode. So, I'd love to hear your thoughts. Are you satisfied knowing that light speed is insurmountable, or are you inclined to challenge it, wanting to understand why it can't be surpassed and how it was proven in scientific history? Leave me a comment. If enough people are interested, I might explore this topic in greater depth in a future episode. That's all for this episode. See you next time.